Can I ask before we start, maybe who has any experience with game development in general? Like any kind of experience? Okay, not a lot of people. And then multiplayer games, probably even less. Okay, some people. That's cool. Yeah, I guess we can start. I'm German. I have to start on time anyway. So yeah, so in the Go community, we talk a lot about like distributed systems and microservices and like infrastructure tools and so on. I want to talk to you or show you a quite different distributed system, which is a multiplayer game, and more specifically the game server, which is written in Go, and then also a way how I'm using logic that is running on the game server, which is Go, in the JavaScript game, because the game is kind of a browser game, and I'm reusing some logic from the server in the client. So we have a lot of stuff to talk about, so it might be a bit fast in some places, so I hope it's not too much, but you can also look at the slides later or talk to me. So who am I? My name is Arne. I work for Delivery Hero here in Berlin. We have a lot of, we run a lot of popular like food delivery platforms. You might know Foodora, Foodpanda, Yemek in Turkey, and so on. We have a couple of 100 engineers here in Berlin, and we have also a booth upstairs. We're hiring. Surprise! I guess everybody in Berlin is kind of hiring. So if you want to do Go at scale and like we have a lot of backend services in Go and really do a lot of Go, please talk to us. But this talk has nothing to do with Delivery Hero. That's just to say now. Yeah, my colleagues call me the angry German, but I always tell them, no, I'm actually just German. Being angry is implicit when you're German. So, and I'm also not a professional game developer, so take everything I say with a grain of salt, because I'm just kind of playing around with this. So the project, the game itself is called Panzer.io. Panzer is kind of the German word for tank, so very innovative name there. But it's just a side project, as I said, very much a prototype, so please see it as that. There are a lot of problems, rough edges, and so on. But the server I wrote in Go, which is called Triebwerk, which I will talk to you about now, is open source. So you can already find it on GitHub. Look at it if you don't understand anything. I would love to hear your feedback, get some contributions, or even just fork it and do whatever you want with it. You should probably not use it in production. Like Go doesn't have a strong ecosystem for games. There's stuff like Unity 3D or Unreal Engine if you want to be really serious about games. It worked for me in this case, but if you're serious about creating a game, this is probably not the right thing to do, but maybe it can inspire you to build something. So that we have kind of a picture in mind, I want to show you the game itself. So this is running in your browser. You are kind of steering this tank you see in the center. Do I have audio, by the way? It doesn't. Okay. Anyway, and the other tanks that drive around there are kind of other players that play on their laptops, and you see them in this view, and you basically just shoot at each other. Rumors say these are Delivery Hero employees that play tank games while working. I cannot confirm that. But yeah, so the goal is just very simply shoot as many tanks as you can. And it's running in the browser, and then has a very low barrier to entry also. That was one of my goals. Okay, so Panzer.io itself, the game, just very briefly, so that we have some context. The game is based entirely on open source technologies, which I will also talk a bit more about, using the web as a distribution platform. So the game itself is running in the browser. You don't need to install anything. It's kind of, the server is lightweight and fast, which was one of my main goals, and the game itself loads fast and is easy to entry. And one of the main motivations I had as well was exploring some of these fundamental multiplayer techniques, which were kind of interesting to me, and I wanted to kind of look into that and also extend my Go knowledge, because this is kind of stuff that I don't do at work at all. Like we build web APIs like most people, microservices and so on, so this was a kind of a different challenge. These are entirely the wrong reasons to build a successful game, by the way, but everybody has to have their motivation, and for me this kind of worked well. So if we look at Panzer.io from the architecture perspective, you have this client application that you see there on the left, which is running in the web browser, And it's a JavaScript application that uses Three.js, which is like a rendering library to talk to WebGL to kind of display the image on your screen or in your browser. And then the server is a Golang application with the only dependency being the Gorilla WebSocket library. And you could even use the standard library WebSocket from Golang. I just thought Gorilla is kind of more full-featured and so on. That's why I used it. And then the server talk to each other via WebSocket over TCP/IP. And any serious game developer will actually tell you that TCP/IP is very bad for multiplayer games because of its properties that are very good for web browsing and so on, like reliability. But for online games, that's actually pretty bad because also for everything that is real-time streaming, TCP is not really the ideal case. But since it's a browser game, WebSockets are the only thing we can use. And then as you see in the middle, the server and the client are sharing some of this core game logic in this WebAssembly module. And why that is important, I will talk about later. And if we zoom out a bit more to kind of how the deployment of this looks, and you have the game as a JavaScript application is on Amazon S3, you access it through your browser, and then the game servers are running on some dedicated machine inside Docker containers. And as I said, the game client talks to the server via this WebSocket connection, but the client and the server also talk to a central API server. The game server talks to it via gRPC, and the game talks to it via gRPC to REST gateway, like to get the server list, and the servers kind of persist all the scoreboards and so on to this central API. But what I want to talk about is just this game server part that you see inside the Docker container there. So this is what I call Triebwerk. Triebwerk is German for like jet engine, I guess, and it's just kind of a cool sounding word. Maybe you can see it as packets coming in, being mangled up and coming out on the other side. I don't know. It's written in Go, obviously, otherwise I would not be talking to you today. And again, just a prototype, do whatever you want. Be inspired, I don't know. Before I can tell you more about how Triebwerk works exactly, I need to very briefly go over some game development basics, as we don't have a lot of people that have experience in that regard. So how games actually work is you have this game loop, which is essentially an infinite loop that runs all the time, which kind of processes your input from your keyboard, from your mouse, applies it to some game state, and then moves your player forward, for example, moves some objects in the world forward according to some physical rules to kind of the next state, and then uses the rendering of the game engine to display that to the screen. And this happens ideally 30 to 60 or even more times per second, so you have a smooth gameplay experience when you have more than 30 frames per second, or even 60 is kind of the ideal nowadays. So this runs all the time. And each iteration then for 60 frames per second has only 16.7 milliseconds to finish this update of the game world and render everything. Now in the multiplayer game, or the one that I'm showing you, this game loop is not actually running inside your game locally. I mean, it is too, but the authority of this game loop is running on the server. So the server is running this simulation, and all your input, if you press a key, it is sent to the server, then kind of applied to this game state, and then the game state is broadcasted back to all the clients who can then show it. This has a lot of benefits to prevent cheating, because we also know this from other applications. You can never trust clients, so they could just tell you, okay, now I'm here, in the next frame I'm super far away, and then as a server you have to kind of try to make sense if that actually is possible according to the physical rules of the world, and kind of do something which is very complex. That's why it's easier to kind of simulate the world on the server and have the authority, and then prevent cheating like that. But obviously you can imagine if every key you press has to be sent to a server and back before you see results, the game will feel latency on every key press. So you really will feel it will not be a good gameplay experience, like steering a boat, because everything is like 200 milliseconds off. That's why in the 90s, John Carmack came up with this concept called client-side prediction and server reconciliation, first in Quake world. Did anyone play one of these old Quake games, by the way, like 20 years? Amazing. You're awesome. I wasted so much time on that in my teenage years. Anyway, this is exactly how it works. And I'm doing the same concept here, which basically means at the same time while the server's running this simulation, the client does the same and kind of predicts what the server would do. And then you synchronize with the server all the time and kind of have to see when the client diverges over time, which it will eventually do because it's a lot of floating point operations and it's non-deterministic calculations. So you will always have some kind of divergence, and you need to correct this ideally a lot of times in very small steps so that the player cannot notice this, so that they don't see, like you see here in this GIF, where you just snap to some other place to have this correction. That's what should not happen, but would happen if you have a lot of packet loss, for example. So this is kind of the idea of client-side prediction, to predict the same as the server would, and then eventually kind of correct the state if it goes off what it should be. Another concept is client interpolation, because the network updates you get about the state of the world are kind of lower than your frame rate. So you don't have perfect information for every frame to show where players are. So what people are usually doing is to kind of interpolate between the two last states that you got from the server and then just interpolate between them over time, which is also sometimes called a conservative algorithm because you're dealing with data that you already know. And you could also do extrapolation. If you know the last position of a player and then the velocity and the direction, you could also tell, okay, now he should be here, and then do some kind of corrections, but that's not what I'm doing in this case. So now we can actually, after we talked about this, talk a bit more about Triebwerk in itself. So first I set some boundaries for the game or for the server to make everything a bit more or less complex, more simple. So everything, even though you have the 3D isometric view, is happening in a two-dimensional space. All the game logic is just in 2D, basically. You can't go up and down with the tanks. It's all on flat surfaces. Input control is only keyboard, because I also wanted people to easily play with the laptop. The map size right now is kind of limited to, this fits like 10, 20 players. I never tried, actually. And slow-moving vehicles like tanks also kind of lend themselves well to kind of this kind of multiplayer scenario. And I also totally wanted to avoid a physics engine, because physics engines, first, there is nothing really for Go. You could maybe get something from C working somehow, but they add a lot of CPU overhead and a lot of, they just use a lot of resources, which I didn't want to get into. So these were kind of the limitations that I set from the beginning. And then if you look at, is this, that's a bit bright maybe. I hope you can see this. So the yellow part down here is the game loop that we talked about, which runs on the server, which then updates the game state, which is the map, the controls, collision detection, weapons, all of this kind of stuff. This runs on the server, and then for each player that is connected to the server, there are two Go routines, one that is writing to, or one that is reading from the WebSocket connection, one that is writing to the WebSocket connection. And then this runs continuously, reading all the input from all players, applying it to the world, and broadcasting it again to all other players. And I will talk to you a bit more about how that works exactly, but this is kind of the basic setup of the server. But then if we have this game state simulation running on the server, we also need to do this actually in Go code. So how the server sees the player is just as a bunch of points, basically. So you have this central pivot point, which is like the player position in the end. And then you have this A, B, C, D points, which kind of make up this rectangle, or what I call a collider polygon, which is kind of what's used to do collision checks between players. And this is essentially how the server sees each player, nothing more than these 2D vectors in the end. And then if you get a movement command to move forward, for example, then for movement you just do kind of a simple vector addition, that you have like point A, for example, which has 2 coordinates, and then you add the direction vector to it multiplied by the velocity, and then you have the next kind of state of this point, and you do this for all the points, and that's how the player moves around. on the server essentially. And for rotation, it's kind of the same. You use the pivot point as like the rotation base, and then all the other points are rotated around this pivot point with some other mathematical formula that you can find online. Like I didn't come up with this, obviously. And that is basically the player movement. Then another important part is collision detection. So if we have these rectangle colliders of each player, of each tank, they can collide with each other or run into each other, and then we need to basically find out when do these polygons overlap. And for that, I use an implementation of something that's called the separating axis theorem, which sounds very fancy. In the end, what it does, roughly, if I understand correctly, is like projecting the edges of each polygon onto its perpendicular axis, and then you kind of compare if these projections from the polygons overlap, and if all of them overlap from the different directions, then you have a collision, otherwise you don't. But in the end, this is also something that I kind of adapted from C++ and watched a YouTube video on it to kind of understand how it works. So no magic there as well. And then for the collisions with buildings, you see a building on the bottom there. I built a small tool that I can kind of define these collider polygons for each building. And I just store them in a JSON file that is loaded on the server and loaded on the client. And then that is also used for collision detection. And the last thing that you see on the bottom right is kind of how a bullet is kind of colliding with a building or a tank, which is just checking if a point lies within one of these polygons, which is actually a much cheaper check than this separating axis theorem. So this is essentially most of the game logic that is used right now and most that I needed for this. One other important part is the data transfer, like how do we actually send the state down to all the players. Like on the right, you see how this could look like a simplified form in JSON. So you have a bunch of positions which are on rotations, which are a bunch of 32-bit float values. And if you would send this for 10 players like this, imagine you have the state of 10 players and send it to everybody as JSON, that would be like over 1 kilobyte already. And if you pack the same 32-bit floats just in 4 bytes and pack everything into a byte array and send it over the wire, it's only 240 bytes. So it's kind of a factor of 5-ish smaller. And this obviously minimizes resource usage of the network, but also of the CPU. You don't need any marshalling, unmarshalling of JSON or protobuf or whatever you want to use. But it also prevents packet segmentation, because on the Internet protocol layer, you have this thing called the maximum transmission unit, which is usually 1.5 kilobytes. And if one of these state packets would be bigger than that, it would be segmented into different of these segments before it's sent over the wire. And then if one of these segments get lost due to packet loss, then TCP kind of stalls the connection and waits for the whole packet to be resent until it resumes, which is also very bad for online games or real-time streaming scenarios. So that is why you will always want to kind of minimize the size of these packets. And yeah, that is kind of the main thing about the networking transfer. And this works very well in the end. If you just have some float values, it can, of course, get a bit more complicated if you have different data structures that you want to serialize. So now the WebAssembly module is kind of using this logic that is running in this game loop that I talked about for collision detection and movement. And all of that is exported into this WebAssembly file. As you can see here, how you kind of compile this into WebAssembly and then how to load it into JavaScript. And then in the last snippet, you can kind of see how to expose one of these functions to the JavaScript scope. And this is to do this kind of client-side prediction that I talked about earlier, to use exactly the same code on the client that is running on the server. And one downside is that it's 2 megabyte, or I didn't get it smaller than 2 megabytes, which is kind of still a limitation of Go. I think the guys are kind of working to improve this. For my game, which is kind of 25-ish megabytes, it doesn't make a big difference. but for your use case, it might be a deal breaker in the end. So that is kind of one downside of this. But it really enables you to run this same code on the client as well. So then I had this problem for WebAssembly, like how do I get the data in and out in the most efficient way? Like I didn't want to serialize JSON on the client and then do that same thing. So I'm using exactly the same way as I'm sending the data over the wire. I'm kind of getting the input, which is just some Boolean values into the WebAssembly, like forward true, backward true, left, right. And then calculating this next state based on the same logic as the server is using, putting everything into this byte array, and then you can copy it over into JavaScript, into a JavaScript byte array, which is called an array buffer there, I guess. And then in JavaScript, as you see on the bottom, you have this construct called a data view, where you can just load this and then read the values back in the same order that you stored them. So here you kind of also have to make sure that when you're writing in little endian byte order, you also have to read in little endian and big endian or whatever. But in the end, this works fine and then is much more efficient than just sending big strings around or whatever. And as far as I know, you can't just take like a Go struct and return it to your JavaScript application and then have some JavaScript object. Or if you can, it would for sure take some reflection stuff that kind of uses a lot of resources. Yeah. Wrapping up then, I created a playable prototype that kind of is a proof of concept that this kind of using WebAssembly on the server and the client works, which is this dream of isomorphic apps that JavaScript developers sometimes talk about. It's not entirely, the game is not entirely Go, of course, but the essential stuff is Go and the server is entirely Go. And it uses like 5 megabytes of RAM and very low CPU right now. I haven't really stressed it yet. And it's based entirely on open source. There are no licensing fees for anything. And it's actually fun. That's like my colleagues that I played with and friends that I tested with actually like the game. So that's actually the most important thing if you create a game. But yeah, for me, it was a kind of a technical project that also should be maybe something that I can release somewhere. So what else? I'm working on some cleanups on Triebwerk. Some stuff is not super nice yet, but you can still already look at it. It's on GitHub on awdng/Triebwerk. That is my GitHub profile. Would love to have some stars, by the way. And yeah, again, you can do whatever you want with it. I would love to get your feedback, talk about some things. Maybe I'm also talking bullshit in some areas, probably. And then, and I also wanted to put some articles out that kind of talk more about some of the details, also about the client implementation, which we can't really talk about here much. Because also nobody wants to hear about JavaScript in here, I guess. So, yeah, for the articles, follow me on Twitter. I will probably put it there. I will also put the slides on Twitter later. And now I actually wanted to play a game with you, but this Wi-Fi situation might be a bit, might be preventing this a bit. So if you have a laptop, you could just go to panzer.io/#s/4p78p, or you just go to panzer.io and then you see a server list, and it would just ask you to register as a guest, and you can just put in your nickname. No GDPR panic, no worries. And then I will actually try if this works. So by the way, the Wi-Fi that I used now is Schwutz Guest 5G. I hope this has the same password though. Did anyone see the password? I don't know. Let's see if we can. How much time do I have left anyway? Okay, it's fine. Let's see if this is also now like a 20 megabyte download, so I may be asking too much of this. Ah, there it is. Okay. But I don't. Is somebody still here who knows this Wi-Fi password? Or does Wi-Fi work for anyone at all?
I thought it is hashtag Schwutz with a big S and big Z and then 40.
Okay. So you mean like this?
Yeah.
Can people try if that works? And then the
Which Wi-Fi?
the Schwutz Guest 5G is what was connected to. see if that works. Success, anyone? Yeah, cool. You still need it? And then just go to panzer.io and then you can see the rest easily. Maybe we can have at least, maybe I can shoot at one of you. That would be nice. Okay, yeah, that can take maybe a minute. I don't know.
How big is the client? Did you say 25 megabytes?
Yes, it's mostly like the assets, like the textures and so on. Oh, actually, somebody is here, I guess. Looks like. Otherwise, I would not be. Oh shit! But this is not good. Yeah, I imagine this could go wrong in all kinds of creative ways. It's not really. Let me see what's going on here. Oh, WebSocket connection is gone already. Okay, that's not good. Let's try again. But we're playing a tank game in the bunker. How cool is that? No? Yeah. Unfortunately, I think this will not be very successful. And now we're all stressing the same small connection, which is probably too much at this point. Okay, then maybe we can let it load in the background. That's it from me. Thank you. And yeah, then we still have some time for questions, I guess. I think we still have like 10 minutes max. Okay, cool. Any questions over there? I don't know.
Can you say how much is the fraction of your own code of this 2 megabyte WebAssembly download? Do you have an idea?
So I think even if you create like a hello world WebAssembly, it's still 2 megabytes minimum. So I don't know what exactly is going on there, but I tried with like just a very minimal version and it's still kind of big. So, but I heard another talk at Go Days at .go last year where they were saying that they're working on to improve this, because if you do the same in Rust, it's much smaller, for example. Yeah.
As we use the same code base for client and server, is it possible to as you use the same code base for client and server, is it possible to implement some kind of different knowledge? So if a client has only a smaller view of the world and is not allowed to know the same stuff as the server does?
Yes, in theory that would be possible. Also, for example, how I do the collision detection right now is kind of inefficient because it's checking all players against all other players. So on the client, you could do things as just like checking players that are more in your vicinity to kind of have lower resource usage. And you could probably also split the map up in different regions, and then the client only knows about parts of it that are relevant to him or something. That should work. One important thing that that's maybe interesting is that the WebAssembly, while it's running, actually has the complete state of the game in its own memory. So it does all the collision detections in the kind of memory that it's running in all the time. So it's not some kind of stateless thing. It actually has all the game state while the game is running. Yeah, back there, somebody? I don't really see you well.
When you are checking collision detection, are you counting delay, being calls or something else? Because several state and your local state are really different.
Yes. That's a good question. Actually, I'm not right now. The thing is that the collision detection is also running locally. So you would first hit something locally, and then the server would tell you that you hit something as well. And it works kind of okay-ish for slow-moving vehicles. But I think if stuff would move faster, then you probably have to take like network delay into account and then kind of play back your state to see if this is a valid collision or something. I'm not really an expert on that yet. So for this, if we have a reasonably low latency, like below 50 milliseconds, it works well enough right now, let's say. You're free to try it out once you have great Wi-Fi. I would love to play a game. Yeah.
Just one more question. Do you have considered using WebRTC for the transport?
Yes, I looked into that as well. And kind of the main, so WebRTC has a data channel that is UDP based, which is why it's very interesting. But it's made for a very different use case for real-time video audio streaming. And there's a lot of setup going on and a lot of handshakes because it's also peer-to-peer based. So would spend quite a lot of effort to get that working, I think. So I haven't really done anything, but that would be a potential thing to explore. Or HTTP 3, aka Quick, which will be UDP based, might also offer something eventually.
Just maybe as a hint, there's a nice Go project called Pion, which is a WebRTC implementation in pure Go. And it is used nowadays also for simple low latency communication from server to client.
Oh, okay.
Setup is actually quite straightforward, and you can then use in the data channel ordered or not ordered to use like low latency data channel transport, which is not reliable, or the opposite for data which has to travel to the client. And this is like a unified transport model, which works pretty well in practice. So maybe worth looking into it.
That sounds amazing. Pion is the name, or?
Pion, just Pion. Like
Okay.
lion, but with P.
Nice, cool, thanks. I will check that. Yes, back there.
Just another suggestion. Great output, by the way.
Thank you.
You can try using TinyGo, which has target like if you compile a Hello World Go program using TinyGo for WebAssembly, that's around like 100 kilobytes or something like that. So you can maybe try experimenting with that and see if you can get binary size down.
Okay, cool. That's also a nice.
I don't know what the limitations are, like if something may be not be available or something, but try that so you can explore the binary size.
Okay, that sounds also very good. Yeah, it's something I haven't looked into it heavily because in the end the game is quite large, so it's not this big difference. But yeah, for if you have a lot of people playing, this would for sure make a difference. Anyone else? Yeah.
How long have you been working on this project?
Yeah, it's kind of the side project, so it's kind of on and off, always some weeks more, some weeks less. I don't know. Hard to say, but I don't know. 100 hours, 200 hours, maybe something like this. I don't know. Over 1.5 years, actually. So it's not. I also don't work on it every day, but I would actually want to release it and people have actually play and then maybe spend money on some gimmicks. I don't know. Let's see. Any other question? I think no. Okay, cool. Thanks a lot, guys. That's it then.